up, guys? New week, new me, or should I say new wardrobe theme for the week. That's right. A couple weeks ago, you guys voted on what you thought the wardrobe theme should be for week 3, and it was a close race, but you guys picked lumberjack plaid. So you're going to get to see me kind of unleash my inner lumberjack this week. This week I'm going to teach you about molecular weight, but before we get into that, I have a little riddle for you. I think you can figure it out. So let's imagine that you have a short train, and what if I told you that the engine of that train weighed 200 tons, the passenger cars in that train weighed 100 tons, and the caboose on the end weighed 30 tons. Now here's my question. With this information, can you find the weight of the entire train? And I know what most of you guys are thinking. What most of you are thinking is, of course we can. That's really simple. All you have to do is take 200 tons plus 100 tons plus 100 tons plus 30 tons. And you added 100 tons twice because there are 2 passenger cars, and that should give you a total of 430 tons for the entire train. Now, what we're going to do this week is something really similar, except we're going to do it with molecules. Instead of calculating the weight of the train, we're going to calculate the weight of molecules. So, just to put this into a little bit of perspective, let's say I've got a molecule, and one of the atoms in the molecule has a weight of 12.01 grams per mole. By the way, the whole grams per mole thing, you don't have to know what that means right now. You just have to know that's how we weigh atoms. And let's say the other 2 atoms in that molecule weighed 15.9 grams per mole. Same question. Could you find the weight of this molecule if you tried? The answer, once again, is probably yes. All you have to do is take 12.01 plus 15.9 plus 15.9, and you would get 43.81 grams per mole. So that is what we are doing today. I'm going to take you through some example problems, and then we'll call it a day. But before we get started, I want to lay out a couple of reasons why knowing about molecular weight is really important for chemistry. What makes our everyday 21st century lives possible are the work that scientists do, like chemists and biologists and things like that. And so one of the most basic and foundational things that scientists need to know about atoms and molecules is their molecular weight. What would be the practical application? What would they need to know the molecular weight of a molecule for? Well, think about if you are a pharmacist, or if you are developing certain medicines. You need to know how much of a certain molecule or substance to put into the medication without harming someone. And so for that reason, you would need to know the molecular weight. Or if you are making fireworks and you want to make it have a certain color of boom, or you want to make it be so big of an explosion, you need to know how much explosive to put in there. And part of that process means understanding the molecular weight. Or if you're a doctor and you're prescribing a certain amount of drugs, that amount of drugs might change depending upon if you are a child or if you're an old person or something like that. And so you're going to need to know how big or small each molecule is so you can calculate how much to give to someone. So if I were to give an overall definition of molecular weight for the purposes of this class, what you need to understand about molecular weight is that it's the overall weight of a molecule. And you can find it by adding up the atomic weights of the atoms in that molecule. So here's a really simple example. Take ozone, which is O3. If I wanted to find the molecular weight of O3, I would just need to find the molecular or the atomic weight of oxygen, which is 16, and then take it times 3, because there's 3 oxygens in that molecule. So that would get me 48 grams per mole. So what I'm going to do here is I'm going to do a few examples, and then hopefully that will get you the idea of what you need to do. Now, I am breaking this down into 3 steps. The first step is going to be figuring out how many of each atom there are, finding their atomic weights, and then adding them up. So the first one is, what is the molecular weight of H2O? This is a really easy one. So first of all, how many of each atom are there? Well, there's hydrogens and there's oxygens. And how many hydrogens are there? Well, there's 2, right? Because that little 2 applies to the H. And then how many oxygens are there? There's 1. What are their atomic weights? Well, hydrogens is 1.008, and oxygen's is 15.9. So in order to do this problem, you're going to need your periodic table. There's one on Google Classroom for you. But what you will be doing here is you will be looking at the bottom number, right? The bottom number in this case. We're going to look at the atomic weight. These are the atomic weights. We're going to add them together. So if I were to do my problem here, right? There's the one for hydrogen. There's the one for oxygen. So add them up. Well, there's one hydrogen. There's another hydrogen. And then there's my oxygen. And so when I add that up, I am going to get somewhere around 18, right? 5, 6, 17. Yep. And I'll just call it 18.01. I'm not sure if that's the actual answer, but I do know that is the answer. You'll get something around that, right? All I did here is I added up 2 hydrogens plus 1 oxygen. That got me 18.01. And so the molecular weight of H2O is about 18. Now, I am not going to be super strict on how many decimal places you go. If you just put 18 grams per mole, that is fine. If you put 18.0, that's fine. If you put 18.02 or whatever, that is fine. As long as you're around 18, you will be good to go. Let's try another one. What is the molecular weight of PO4? Well, let's do this. How many of each atom are there? Well, if we look at phosphorus, there's only 1. But if we look at oxygen, there is 4, because that little 4 there applies to the oxygen. What are their atomic weights? I would look that up on the periodic table. Phosphorus is 30.9. And oxygen is 15.9. And so what I would do is I would just set up my problem. Now, when we get to bigger things like this, we might not just want to write down the weight of oxygen 4 times. And you'll see what I mean when I get there. But see, what I'm going to do is I'm going to take 30.9. And then what I'm going to do now is I'm going to do a separate problem here, right? What is 4 times 15.9, right? When I take 4 times 15.9, I get 63.6. So what I'm going to do is I'm going to add 63.6 to my 30.9. When I do that, I get 94.5 grams per mole. And like I said before, grams per mole, you probably don't really understand what that is right now. You will later on in this class. But for now, you just need to know that's how we measure the weight of atoms and molecules. So 94.5 is our answer there. What is the molecular weight of H2CO3? Right? Well, how many of each atom are there? Well, we've got 3 atoms, right? We've got hydrogens, we've got carbons, we've got oxygen. So how many hydrogens are there? There's 2. How many carbons? 1. How many oxygens? 3. All right, so we're going to use this to set up our problem. Let's start with hydrogens, right? Hydrogen has an atomic weight of pretty much 1, right? And so what we're going to say is we're just going to call it 1, right? And so if there's 2 hydrogens, that means that there's 2 total, right? It's like 2.02. All right. There's 1 carbon. So I'm going to write down 12.01. And now we have oxygen, which there's 3. Right? So what I'm going to do is I'm going to, over here on the side, I'm going to take 15.9 times 3. And I get 47.7. So what I'm going to do is I'm going to add 47.7 here. And then I'm going to add up all my stuff. So I've got, and I'm just using a calculator for this. I'm taking 2.02 plus 12.01 plus 47.7, and I get 61.73. So H2CO3 should have a molecular weight of 61.73 grams per mole. Another one. Now we have parentheses, and hopefully you remember from last week what the parentheses mean. The little 2 applies to whatever is to its left. And so that means that the 2 applies both to the oxygen and to the hydrogen. All right. So how many of each atom are there? Well, we've got magnesiums, we've got oxygens, and we've got hydrogens. And we only have one magnesium, we've got 2 oxygens and 2 hydrogens, because there's OH, but we're saying that there's 2 of these, right? And so that means there's 2 oxygens and 2 hydrogens. What are their atomic weights? Well, they're right here, 1.008 for hydrogen, 24.3 for magnesium, and then 15.9 for oxygen. So let's look at this. So magnesium, there's only one of them, so there's 24.3. Now there's 2 oxygens. So what I'm wondering here is what is roughly 16 times 2? Because this is almost 16. What is 16 times 2 since there's 2 oxygens? And the answer here is that's going to be about 32. How many hydrogens are there? There's 2. Each one weighs about 1. So I'm going to say that's 2.0. All right, so I get 0.3. I get 8, and I get 5. So that means that MgOH2 should be 58.3 grams per mole. Just remember the sort of nuances that go along with these formulas, with the parentheses and the little numbers and stuff like that, and you should be okay. Your assignment for this week is pretty straightforward. What you're going to be doing is you're going to be going to Google Classroom, and I've given you 5 questions, 5 molecular weight questions for you to do. I want you to do these on a separate piece of paper, but make sure you use a dark writing utensil like a marker or a Sharpie or something like that. Afterwards, I'm going to have you take a picture of that separate sheet of paper and upload it to the assignment so that I can grade it. Remember, if you have any questions, we have Q&A sessions on Zoom from 11 to 11:30 a.m. on Tuesdays and Thursdays. You can also text me on Remind or get a hold of me during my office hours every day from 1 p.m. to 2 p.m. See ya.